PAF512. Welcome this week's module 1. We will be going over interrupted time series. This module and the lab are fairly straightforward. It's a pretty easy one to grasp and get your head around. Two things I want to lead with from the beginning. If you get stuck in the lab at any point, I will strongly advise you to come back to sections 2 and 3 of the lecture because they virtually, with using different data, show you exactly what you need to do to accomplish the lab itself. So come back, make sure you're referencing these sections if you get stuck at any point. Second is if you do have any issues, errors, be sure to check out the GitHub issue tracker, the Get Help link from Canvas. Before posting your question or issue, always check and see if somebody else has posted it on there as well. We want to avoid any kind of redundancies. That way we can make it easier for students to find answers to what they're looking for in the situation or in the event that another student has already asked it. So once again, to recap, number one, if you get stuck in the lab, come back to the lecture, particularly section 2 and 3, and check those sections, and that should help you break through any kind of walls you might have during the lab. And then number two, don't be afraid to use Get Help, the issue tracker. Just make sure before you post a new question that you check to see if that question has already been asked and answered. All right, well, let's get into it. So interrupted time series, we're going to cover the overview material, and then I'm going to leave it to you to jump into the lab. I do have a faux scenario about sales and marketing figures that I'm going to go through, and it basically mocks up what you'll come across in the lab itself, just using different data to show you sort of how to go through that. All right, so interrupted time series, what is it? When do we use it? What's it for? Interrupted time series is really helpful if we want to gauge the immediate impact as well as the if there was a sustained effect from our intervention. Now, some of the criteria we have to have in order to have an ITS, interrupted time series, be applicable or appropriate is we must be working with longitudinal data that can be collected daily, monthly, yearly, whatever interval. We just need data over time, both plenty pre and plenty post, in order to have a valid assessment. And then we have to make sure that our intervention, it did get rolled out at one specific point in time. So you will see in this lecture two different scenarios. One that we'll look at first is going to be tobacco consumption over time. It's an annual measurement, so you'll have a certain value per year. And the second is going to be looking at being class that is rolled out in school. So it's measuring students' overall well-being, with the intervention being a class that was then offered to ultimately help improve well-being. And so those are the two we're looking at. We have a collection of data over time, both of which, or excuse me, the tobacco option is, I believe, 20 years of data. The well-being, we'll get into it. Don't let me get ahead of myself here. But ultimately, you'll need it to be rolled out at a specific point in time. So the policy intervention for the tobacco example is at year 10, a tax was implemented. So that was at a particular point in time. This intervention occurred. With the well-being class, it was when the class started. That is the moment in time when the class began. So we need to have a clear moment in time where the intervention occurs. And then ultimately, just the more data before and after, the more robust our results will be. So moving on into it, we're going to first go over the 4 possible outcomes of our analysis. So first, again, this is the tobacco consumption. So tobacco consumption over time, measured annually, we have 20 years total, so up to 10 years, which is the pre-intervention trend. This is what we're looking at here. Now, one possible outcome of our model of our interrupted time series could be no policy effect. And visually, that would look like just a continuing trend of the pre-intervention slope. Our policy intervention takes place at year 10. Again, that is a tobacco tax. And we see that there's no change. It doesn't appear that there's any immediate effect. There's no change in the intercept at the point of intervention. There's also no change in the slope. So we would consider this no policy effect. Another potential outcome is an immediate policy effect, but not a sustained effect. And what that looks like is a break in the intercept at the point of intervention, but the slope remains basically the same. So again, that's an immediate policy effect with no sustained effect. Opposite of that is going to be a sustained effect with no immediate effect. So at the point of policy intervention, there is not a change in intercept. However, there is a change in the slope after the policy itself, the intervention, excuse me. So this is a sustained policy effect with no immediate effect. Now here's where we could have both. So in this situation, we have both an immediate effect, the break in intercept, and a change in the slope. And in this situation, that's great. That means that there was less tobacco consumed, great for public health, as well as a continuing decrease over time. All this to say, in this instance, the tobacco tax was beneficial. Coming down, now looking at the statistical model itself, what you're going to have to do in the lab is you're going to have to work with some basic data, and you're going to have to come up with or create a few new variables. So just to preface it, your lab will provide you, and you'll have to create your own R Markdown document. Make sure you're keeping it clean, readable. That's very important for grading purposes. But ultimately, you're going to be given this data. And from this data, you're going to have to create additional variables, which we'll go over now. So the model is going to be looking at our outcome variable, which in the case of, let's kind of jump ahead to the well-being example, that's going to be the measurement of well-being scores, which is students doing a survey tells them what their well-being score is, and that's measured over time. So that's our outcome variable, whatever we're measuring. Beta 0 is going to be our intercept. T in this instance is going to represent time. Time is going to be a continuous variable, and again, it can be days, months, years. In the case of our tobacco example here, time is going to be representing each individual year from 0 to 20, 1 to 20. So that's going to be 1, 2, 3, 4, 5, etc. In the case of our lab's going to be daily measurements, and it's going to be 365 observations. So our data is going to be 1 through 365 for our time variable. So the time variable, again, t, in this circumstance here. Now we have our dummy variable, and each of you should have, if you followed my announcement and remember from your previous courses, I believe it's on program evaluation, perhaps it was research design. At any rate, your previous courses leading you up to this went over dummy variables. In this case, our dummy variable is going to be very straightforward. Anything prior to the date of intervention is a 0. It's toggled off. Anything post intervention, including the day of, will be 1. That's going to be toggling that on. So pre-treatment, post-treatment. D in this circumstance is representing the treatment variable. Forgive me, I may have said time as well for beta 2. It is treatment. That's our treatment flag. So that's our dummy variable, 0 or 1, depending on if treatment occurred or if it has not. And last is going to be our time since variable, labeled P here. This is also a continuous variable. It's a little different though. Anything prior to intervention is 0. However, anything after intervention, so the date of intervention, will be 1. And then for every additional observation thereafter, or every different unit in time, so in this case here, we'll call this days, so day 1, 2, 3, now let's call it years. Year 1, 2, 3, 4, 5, 6, 7. Year 4 is when treatment occurred, so that's labeled 1 for time since. Year 5 would be time since 2, that's when the next observation takes place, and then so on and so forth. So again, circling back to the lab, time since in the case of our treatment here, our treatment takes place at, oh, pardon me, we don't have the treatment here. Treatment doesn't explicitly show in here, but treatment I believe is a date 121. Yeah, 121. But that's not listed in here. But at any rate, hopefully that makes sense. For every day or every instance following the treatment date, you're just going to be adding 1, and that tells you how many days after. And that's very helpful when we're going to be determining our predicted values. You know, say day 50 days after treatment, what is our predicted value? And then also it helps us to determine what our counterfactual is. So time since, treatment, time. Those are going to be the values or the variables we will be working with here. Now, visually looking at each of these, so beta 1, this will be representing our pre-intervention slope. Again, beta 1 will represent time. So when we look at our coefficient tables, which we will shortly, this will represent time. That value will show the trend prior to intervention. That is our pre-intervention slope. Now, beta 2 will be representing what we will call the immediate effect, which we went over briefly. Again, that's going to show if there was an immediate change at the time of intervention. And that will be represented by the treatment coefficient, if that's what we label it, but that's what we label it in our lab. So the treatment coefficient, beta 2, and then finally we have our beta 3, which is going to be our time since variable. Now, very important, you want to pay attention to this. The time since coefficient, when we look at our tables, it does not represent the entire post-intervention trend. What it does is it represents the difference between the pre and the post slope. So in order to get the actual post-intervention trend, if you want that at any point, you need the combination of these two. It is not simply this. So once again, just to recap, beta 3, or the time since coefficient, is going to represent the change between the pre-intervention and the post slope, or the difference. And so you'll need a combination of those to see what the actual post-intervention slope is. Now, just putting it all together, beta 1, time, pre-intervention slope. Beta 2, treatment, immediate effect, if any. Beta 3, time since, the difference between the pre and the post slope. All right, moving on to the counterfactuals. You should remember the counterfactual is the uh, value that would exist had a treatment not taken place. So we'll go through this in a lot more detail later in this video, but to cover that, all we want to be looking at is if we toggle our time since and our treatment to 0, and we plug in time only, that will tell us what our coefficient, or excuse me, our counterfactual would be, and you'll see that here. If the intervention had not occurred at a specific point in time, let's say 18, if we do this, this will determine what our value would be at year 18 had intervention not occurred. So on this same trend at 18, where would we be? And then opposite of that again, if we wanted to find the value at a specific point in time, the predicted value at a specific point in time, we would use the time, let's call it 18, as well as dummy variable turned on. Again, dummy in this circumstance is going to be the treatment variable, so we turn that on, so that's 1. And then as well as the time since, we would have to do the math on what that would be. So that would be, I believe, 8. And down here, that's exactly what we're doing. So we're looking at year 12. What is our counterfactual? We have our predicted value, and we have the equations for those. And this gets a little bit more clarified as we move on to this actual example. This example, read through this. Please don't only use this video. Please read through this. It'll be far more helpful. But to set the stage, we're looking at measurements of students' wellness scores and how a policy intervention, which is a mental health education class, impacted those scores. So a couple values we need to know about. In this data set, we have 365 observations, each representing a day. Then we have the index score, which could range from 0 to 300. That's the well-being index. And then we have our intervention time, which is at 201, which is when the students will start to attend this class. And you can actually get this data and do this yourself if you want to. So we're going to be looking at a few things here. We have the time variable, which again, in this case, will be 1 to 365. We have the treatment flag, which is 0 prior to treatment, 1 thereafter. And then we have our time since, which is 0 leading up to treatment. And then on the date of treatment toggled on, every consecutive observation thereafter is 1. And this is 1 for every day. So for every day, 160 days past treatment, we would want to be able to see what the values would be. And here's similar to what we looked at before, just another way to visually represent it. We're going to be looking at how to interpret the summary table, the coefficients for this type of model. So as mentioned, we have time, treatment, time since treatment, and then of course the constant. Or the intercept here. So now time. Time is going to be simply the pre-intervention slope. Let me make sure I put that here. Pre-intervention slope. Okay. This is the trend that was occurring prior to intervention. So in this case, we can see that over time, students' well-being scores were actually increasing on their own by 0.19 per day. Now treatment, this is the immediate effect. You'll just want to remember it as that, the immediate effect. So we can see when the day classes rolled out, we noticed an immediate increase in the well-being scores by 13. And it is statistically significant. So we can attribute the increase to the class being rolled out. And then last, our time since treatment. This is going to be representative of the change in the post-intervention slope. So this is simply the change. So what that would mean is the 0.54, which again is statistically significant here and an increase. That means that over time, the slope increased by 0.54. So this added to time means that would be the total post-intervention slope, or the post-intervention slope in total. This is simply the change. So there's an increase of 0.54, and again, statistically significant. So we can say by this this assessment, the well-being classes or the emotional health, whatever it was, the well, let's double check it. The mental health education class was effective both immediately and in the long run, as much as long run can be for only 365 days of observations. It was effective. So now we're going to be going into some of the nitty gritty with determining counterfactuals. A little bit more explicitly, at least in terms of what you need to know for the lab. But I did want to touch on part of this here. And to recap again, I'll say it one more time for you. This is the area you want to come back to, one of the areas if you get stuck in the lab. Again, this will very, very efficiently guide you through what you need to do in the lab. All right, so the counterfactual. So let's look at some of these situations. Forgive me, there's a spot that I wanted to get to. It's what I was looking for. I passed right by it. So let's say we want to look at the counterfactual. Once again, the counterfactual is the value that we would expect if the intervention never. So that means that treatment is toggled off, therefore it's 0. Time since is toggled off, therefore it's 0. And then we have a moment in time. So we're going to be using a couple of things here, and you'll do this similarly in the lab, so just keep all this in mind. So let's say at time 230, day 230, we want to determine what the score would have been had the intervention not occurred. We will classify this as in this data set, it's t equals 230. In yours, I recommend using values time, treatment, time since. They're just easier to interpret when you look at the tables. So all that to say, we want to look at day 230, without intervention, what would our value be? And this is how we would structure that. Following this, and you'll do this in your lab, in order to determine our counterfactual, you're going to use the predict function, the data frame that you save your model to, and then this new frame, or this new data frame that you've created for the scenario of your counterfactual, which again is the time equals 230. I'll go over this a little bit more, I guess you can call it layman's terms, in an example I'm going to go through with you here shortly. So on your own, go through some of these. There's even some things to consider, delayed effects. We won't talk about those necessarily in the lab. There is one question, I believe, that this may have something to do with it. But ultimately, one thing you want to pay attention to if you're looking at running an interrupted time series analysis is the context of the intervention. Let's say that, I think it's actually one of the things we'll look at later. But ultimately, we want to look at how a worker training program helps income for those who attend it. Something like that may not have an immediate impact. It may generally take a few months to kick in, or something more familiar to myself. Part of my capstone for the program before I graduated, I did the capstone. Each of you will. I worked with the city of Phoenix to determine if a homeowner association water efficiency program they had actually had an effect on reducing water or improving conservation. And so that was an effect that went into play. So it was basically one initial treatment where it started, and then the HOA most likely would not implement it right away because there's a few things they would have to do first. So all that to say, in a situation, or situationally speaking, you may have a delay effect where you don't want to have your treatment day be the exact same day the treatment occurred. You may want to take a more practical approach and say, well, this may take a month or two to really implement. So let's have our treatment date be postponed by 30, 60 days, whatever it may be. So that's something that you want to take into consideration depending on the context of uh, the situation or the intervention. So that's something to read through here, not directly applicable to our lab though. Now, before I move on to the lab and the faux example I put together for you, this is the last section I want to recommend. The replication of a study, this is going to go through in grave detail a way to build out and structure your analysis, and some of this will be almost perfectly repeatable or translatable to the lab. So spend some time going through this, and then one final thing is there are some big issues that you can run into when it comes to running an interrupted time series analysis. I won't go over those in the video, but you do want to make sure you read through these. So autocorrelation teaches you also some functions and some methods you can use to test for it. Um, again, timing of the intervention. In fact, in the lab itself, there's a bonus question, completely optional, but you can get some bonus points for it. If you choose to do it, it talks about a time series analysis with a control group, and that is demonstrated here towards the end of section 3 in the lecture notes. One final thing too is something called the regression to the mean. Let's say that there was an immediate effect, but then things tend to return to their norm over time. So this is also something to look out for with an interrupted time series. So we're done with the lecture here. I'm going to preface the lab. The lab itself is going to be looking at a policy problem where you have a city that is trying to increase its bus ridership, and they implemented a more frequent schedule. So the more buses, more ridership, that's what they're looking at. And ultimately, you're only provided with this data. As I mentioned before, you have 365 observations from which you will need to um, create your necessary variables. So I have a faux example here that I'm going to go through with you. So welcome to my R studio. So in this example, it's going to parallel what you're going to do in the lab, but this is just different data showing you an example of how to go through it and some of what I expect in terms of formatting, um, how to structure it, how to answer the questions. So, all right, moving on. Don't let me get stuck here. So in this scenario, we're simply looking at a less public policy, just sales and marketing. So we have a company who sells products online, and they rolled out a marketing campaign. And we're just simply looking to see, and they rolled it out on one day. So it was one hard start. And we have a time period of 365 days. We have our intervention date, the treatment date of 182. And then we just generally are looking at to see if the marketing campaign increased sales. So ignore this gibberish. This is just something that was put together to generate some mock data. So we have a date, which we won't actually use this date category. We're going to create our own time category, but then we just have sales. So we have all the sales listed over time. And again, 365 observations. So first thing we're going to have to do, and same thing you're going to have to do in our lab. Okay, so the lab itself, again, is going to be asking you to create, as part of question 1, you need to create a time, treatment, and time since variable. So we're going to have to do the same thing in my faux example here of the marketing campaign. And then we're also going to be needing to provide a summary statistics of that data frame. So looking here, first thing I have to do, I know that I have 365 observations. So the first thing I'm going to do is from my data frame, I am going to add a time column, and I'm simply going to do 1 through the number of rows that exist already, which is 365. I need to create my treatment variable. And again, just to reemphasize what I've already mentioned a dozen times, uh, this is almost exactly how you see it in the lecture. And you'll see that throughout this whole course. Every module, basically, the lecture translates very well to the lab. So it's a very straightforward course. These videos are honestly possibly superfluous. However, they can be helpful for those who like to see it visually and be sort of guided through it. All that to say, it's almost exactly the same as you see it in the lecture. So read the lecture thoroughly, do the lab. If you run into hurdles, circle back to the lecture. Okay, so now I need to determine or create, excuse me, my treatment flag. So I create a new column, treatment flag, and then the if else function, you should be familiar with it. So we're saying if the time, the value, the observation in the time column is greater than or equal to 182, because again, our data, our treatment, excuse me, is day 182, day 182. So if it is on or after day 182, we want a 1 in that. If not, it's a 0. So again, Post-treatment flag is 1 for anything after the treatment took place, and 0 prior to. Pretty straightforward. Now we want a time since column, and that's going to simply be, it was just easier to do it this way. We're going to be inserting 0 all the way in all the rows through 181, everything prior to intervention. Following that, we're going to be inserting 1 through 184, altogether totaling 365. And we'll see here, just to show you the data, this is what our data looks like. The date column, you can just ignore that. We have our sales column in this example. Time, treatment, time since. So we'll scroll down and we'll get to the point where you can see the treatment occurs on day 182, our flag goes on, and our time since starts. So for every additional interval, we get 1 added to it, and then we end with 365 observations, 184 days time since is our max, and so forth. So coming back, this is something super important that I wanted to touch on. For those of you unfamiliar, I don't recall how often Stargazer was used in the previous courses, but it is used here, and I need you to know exactly how to handle this. So Stargazer is awesome, creates very clean looking tables, especially summary tables for when we do our models. So Stargazer is pretty simple. You can get more complicated, but really for our purposes, I'm okay if you just do the very basics. You can include your data frame. Type is text. This is what I really want to harp on right now, and I have it notated in here. When working with Stargazer, in your RStudio environment, prior to knitting, all you need to do is set type to text. However, and a big however, before you knit your final markdown, and especially before you submit, I will be watching out for this, and you will be docked points if you don't do it correctly. If you excuse me, backtrack. You need to before knitting do two things. You need to switch text to HTML, and you need to make sure that you put in your chunk parameters results equal as is. And now what that's going to do, so this was already printed out. This is the text option, so type equals text. So this is very great for if you're working in R and you want to see what the table would look like. So keep it as type equals text in R, and you can see what the results are there. But if you switch it to HTML and as is, you're going to get this nonsense, which makes practically no sense. So what you're going to want to do is just change this. And sorry, this translates really well when you knit the document, so it creates a nice clean table in an HTML document. So that's the reason you want to do that. So big notice there. Make sure that you go through and do that correctly. Now coming down, so that's question 1A and 1B. So question 1A is creating the variables. Question 1B is printing a summary statistics, which I want you to do in a Stargazer format. Question 2, we're going to be running the model and providing the table in Stargazer. So first we're going to create the model. LM, very simple. We have the LM function, pardon me. We have the variable we're looking at, which is the sales. And then we want to do a little squiggly, and we're looking at time, treatment, time since, and then of course data equals our data frame. And we're just saving that to the regression interrupted time series. So now we want to view our results. Once again, same thing here, Stargazer text, change it to HTML, and then also include the results as is before you knit your final document. Now, in this circumstance, we're looking at time. So prior to intervention, there was a significant increase in sales over time. The treatment itself, again, this is the immediate effect. Treatment represents the immediate effect. There was an increase. However, it is not statistically significant, and we'll actually discuss that shortly here. Time since, there was an increase, a very small increase, and it was not statistically significant. The constant, that represents the intercept, and that's just saying it is significant because it's different from 0. So you can virtually ignore that, but we need that for plotting purposes. That's where our y-intercept would be. Now coming down, this is how I want you to structure your responses. It'll make it easier on me for grading, so I would really appreciate your cooperation. In the future, I'm getting ahead of myself. I was going to have a template for everybody to use to make life easier, but that's neither here nor there for this course. For question 2B, what does the intercept represent? We already went over that. That's going to be, again, just the average sales prior to the intervention. Ultimately, it's our y-intercept. Question 2C, what does the coefficient of time represent? This should be straightforward, so this probably seems repetitive. Feel free to skip ahead. The time coefficient represents the slope of the line prior to the marketing campaign. It shows the sales were increasing or decreasing before implementation. In our case, it showed that sales were increasing over time before implementation. Okay, now question 2D, which coefficient represents the immediate effect? Everybody knows the answer. It is beta 2, or treatment as we've categorized it, that represents the immediate effect, if any. And then last, the coefficient that represents the sustained effect of the policy, that will be the time since value coefficient, which is also beta 3. And that represents if there was a sustained effect, which in our case, there was nothing significant to be mentioned. Now, question 3 gets more into the interpretation and direct applicability of what your tables will be, your outputs will be in the lab itself. So in the situation of this marketing campaign, our coefficient for treatment was not great. I mean, it was an increase, but it wasn't statistically significant, so it's difficult to attribute the effect to it. Now, next, the marketing campaign increased or decreased sales in the longer term. That's looking at the sustained effect. In our case, no. Although it did, there's a very, very small increase. It was not statistically significant, so we can't attribute it to the marketing campaign. This one right here is going to require a little bit more out of the box thinking. So I want you to really think about it and give me whatever your perspective is. In this situation, we want to provide, excuse me, a brief possible explanation for the results. So in the context of the marketing campaign, and we can get more nitty gritty with it, looking at when the dates were, was the treatment close to, say, Black Friday rollout or traditional sales time, and so we want to consider what other variables may be at play in the bigger picture. So in this example, there was an increase, but it wasn't statistically significant, which means that there's some noise. So there's some kind of confounding variable that we're not accounting for that may be to blame or the cause of the spike, but without significance. So perhaps seasonality is an explanation. So I don't expect anything too crazy, but definitely get those wheels turning and let me know if you have any creative thoughts on it or if there's anything that stands out in the lab itself. All right, now we're going to be doing a counterfactual in this section here. So this is where I want to get a couple things important, and I want to circle back to the lecture briefly because the lecture, pause for a moment, I'm going to find the area that I need to find. So no time lost for you, but a little bit of time for me. So I wanted to find this area to go over it with you. So when we're looking at our counterfactuals and trying to determine what values would be at certain points in time based on our model, there's a few things we want to keep in mind. So I'm circling back to the lecture here. Let me get my little handy dandy drawer out. And this is going to be section 2.1 if you need that for reference. So in this circumstance, this is again going back into the mental health education class and the well-being of the students. So we want to look at different points in time to see what the values would be, so the well-being scores that we would expect. So we know that the treatment occurred on day 201, and we want to look at the first day. So time 201, and then that would make our time since treatment equal to 1, because it's the first day of the treatment. And this is going to be our model. And now we want to come down here, and this is where we're going to pay more attention to it. So day 201. Oh, forgive me, everybody. This is not exactly the one I was looking for. This is what I was looking for. Okay. So let's say we want to look ahead. So we want to look 30 days past treatment uh, to see what the well-being scores would be in that instant. So we want to know our time since treatment. And of course, the treatment itself will be um, on or 1 if we're looking at what the predicted score would be, or if we want our counterfactual, that would be off, and time since treatment would be off too. So looking at 30 days past treatment, we know that our treatment occurred at time 201. And so I just want to point this out because it can get confusing for some. So we want to look 30 days past treatment. So that's really easy. We always label our time since as 30, or as you'll see here in the R Studio, time since I wanted to look 50 days post treatment. So I simply put in 50 days post treatment. And this is ultimately how we find these values. So you'll need this for the lab. So time since is 30, treatment is on, but you'll notice that 30 days after 201, when the treatment occurred, 201, 30 days after, you may think 231 for your time value. However, I want you to remember it's the most simple, straightforward way to do it. In this circumstance, when you're looking into the future for how many days after treatment, you're going to want to do time plus time since, in this case, the number of days after we're looking at, minus 1. So instead of getting mixed up, because you'll get a wrong answer if you do this, and I've seen it before, you're going to want to put the time since, the days you're looking after, treatment on if we're looking for the predicted value here, and then the time that the treatment occurred, excuse me, I should clarify that, treatment day. So the day treatment occurred plus the time since, and then subtract 1. If you do it otherwise, you're going to be losing a day or off by a day, and your values will be different or wrong. So keep in mind this. If you need to, circle back to this to reference how to set this up correctly, or this video, and you'll see how I do it here in this circumstance. So in this circumstance, we had our treatment day, or this example of the marketing campaign. Our treatment is day 182. So coming back down, day 100. Nope, where did we lose it? 182. So we want to look 50 days past that. So we set our time since to 50, our treatment on, and then we take our treatment date, which is 182. We add the 50, brings us up to 232, but then subtract 1. So our time value will be 231. And in case you get stuck, this may seem silly, but it can get confusing for some students. You can go to your data, and you can simply look at time since column. And again, we want to look at 50. So time since 50. Our time is actually 231. So that's another way that you can make sure that you're getting the correct time value for the time since value that we're looking for. Okay, a lot of that. And now use this for your lab. So you're going to establish a data frame, do a cbind on these different items, save it to a new data frame. Then we're going to use the predict function using the regression model we built, and then the data frame that we're saving this to. So data 50, just representing 50 years since treatment. And that ultimately will give us the value that we're looking for. So at 50 days past treatment, the value we expect, the sales numbers we expect is 73. We'll call this in the tens of thousands, so 73,000 or thousands, whichever you prefer. Doesn't really matter. So keep that in mind when you're doing these next questions. You can pause that momentarily. I had previously typed in the wrong answer there, so I had to correct that. So to recap, 50 days after treatment, our predicted value would be 73.04. Therefore, and do this in your, make sure you bold your answers like this to make it easier to read, 73.4. So the sales number 50 days after intervention, this is how you accomplish that. Now we want to look at the counterfactual, and that again will be here in section 2.2. As I mentioned multiple times, it translates very thoroughly. So always circle back to the lecture sections and it'll tell you almost exactly what you need to do. So now we want to know the counterfactual for 50 days out. In order to determine that, we're going to do the exact same thing, but we will toggle treatment off and time since off, set them both to 0, and that will tell us if intervention had never occurred, what would be our sales value. And we can see here when we run it, we get a value of 72.03. So if intervention had never occurred, our sales would only be, um, if we take it at face value, $1 different. So we can see a little bit more into why it's not significant after all. Okay, pause you guys again there so I can answer this next question. So we're going to be doing the same thing. We just need to look at the counterfactual for 100 days. So now we're going to restructure it, save a new data frame. So as you can see, all I've done here is I've changed my time because it's a counterfactual. We always want to set our treatment to 0, time since to 0, and then again run the prediction function, predict function using our summary or our model on the data frame we just built. And to recap one final time, if I'm looking at 100 days after intervention, my intervention occurred on day 182. I want to make sure on day 182 100 days after intervention, which would technically be time since 100, what is it, 281, 281. So 100 days past intervention would be time 281. I might be harping on that, but some folks get stuck on it. So I just want to be really transparent, tell you to keep an eye out for it, help make sure you get the right answers. So 281, not 100 days, not 100 plus treatment date, 100 plus treatment date minus 1. So 281, and then ultimately we get our answer here. If the intervention had not occurred 100 days after treatment, 100 days after what would have otherwise been treatment, our sales would be 76.69. Now, for the last question, I didn't type up the answer here, but I'll go over it with you verbally. Are the two counterfactuals the same? What do you think? No, of course the counterfactuals aren't the same. You have two different points in time and you have a pre-existing trend. So you have a trend. In our case, we had an upward trend where just as the days went on, sales were increasing by 0.09 every day. So 9 cents every day. So we know that at two different points in time, 50 days after versus 100 days after, what otherwise would have been treatment, our sales would not be the same. So the counterfactuals in this case would not be the same. They're two different points in time, two different points in time on a slope. So to answer that question, no, they wouldn't be the same in this situation. All right, well, that's hopefully okay. I ask for your grace because this is my first time recording some video lectures. If you have any recommendations, advice, suggestions on how we can make these better, I would love to hear it. For now, though, that is everything you need to know for the interrupted time series regression model, the lab itself, and then the walkthrough. This should set you up very easily for the lab assignment itself. Thank you very much for your time, everybody. Take care. Reach out if you have any questions. Bye-bye.